Dear students, so today we start discussing our lecture 3, or not really lecture 3, chapter 3 should be the third part or the last part of your study, because the time is too short to make a whole gamut of study, because we are doing things in pretty details. So that has to be understood, that our detailing is huge, and the amount that we covered in convexity is a huge amount we have considered, and I'm sure you would agree with that. So today we are going to start our discussion on constant optimization and multiplier rules. Now, constant optimization is a key thing in real applications, because in real applications the variables has to satisfy certain kind of constraints. And please understand that the beauty of constant optimization lies by first realizing that a linear function can never ever have an unconstrained minimizer. A linear function is always unbounded on on the whole domain Rn. I leave that to prove to you. Just think of the function y equal to x in your mind's eye and you immediately understand what I mean to say. So here we are going to now talk about a function f which is differentiable, which we want to minimize over a closed convex set. Okay. You might be wondering why I am talking about closed convex sets, because closed convex sets are the ones which have uh, the closed convex sets are the ones for which we have which appears in real applications largely. You might ask, what would happen if the set is open? We will consider the situation when the set will be open, but we will use our idea of a closed convex set in order to get a result there. So that will come later on as we go on discussing these issues. So here is a problem. I'm sorry I couldn't give you the text file. The text file has been typed just because there's too many things at the same time. So I hope you would be able to read this kind of notes. So here I either minimize or maximize a function subject to some x in C, where the function f from Rn to R is a differentiable function and C a closed convex set. So we are now first asking, whenever you have a optimization problem, we need to first ask, what is the associated optimality condition? That is, first we must know what is the necessary optimality condition. So we have to get kind of an equation in inequalities whom we have to solve in order to first get a candidate for which we can say whether it after candidate, and having that candidate we can say whether it is a maximizer or minimizer or whatever. So that kind of condition we have to come in this case. Now in this case, constant optimization things are slightly tricky. Like if you have a local maximizer or minimizer or differential function over whole of Rn, then grad f x star equal to 0 is the necessary condition, whether you take you want to look for a maximizer or a minimizer. But here the situation changes, and normal cone that we have learned in the last lecture on convexity, normal cone to a closed convex set, becomes a vehicle which drives this whole process. So here the conditions are slightly different for the maximum and that for the minimum, a sign difference actually, but still it is a significant difference. So here is our first theorem, which says that if you have a local minimizer x star for the function over this function p, right, then if x star is a local minimizer, then necessarily the negative of the gradient of f must be a normal vector to C at x star. If f is convex and the condition A, means this condition actually holds, then x star is a global minimizer of f over C. Now, being a local minimizer, it mean that, okay, in a small neighborhood around x star, a neighborhood whose intersection with C is non-empty, we can find such a neighborhood on which the function f is the function f is minimized at x star. That is, for all elements of that neighborhood, fx star has the lowest value. At other point, the function value is higher. So here, just if you look at the proof, that is what we say, that if x star is a local minimizer of f, by choosing any x element of C, now you can use the convexity of C to construct an element x star plus lambda x minus x star, where lambda is between 0 and 1. But you can choose it so small that, because you have joined x and x star, it is the same type of argument that you had for showing that a local maximizer of a concave function over a convex set is a global maximizer. So what you will do when you make lambda very, very small, that you put lambda comes, when lambda is 0, it is equal to x star, this whole quantity. When lambda becomes very, very small, this x star plus lambda x minus x star is very near x star, and hence this part is in C, and then I can easily show that I can make lambda so small that this part goes into the intersection of the ball and the set C. And hence, because it's a local minimizer there, this is true. And now you apply the definition of differentiability of f and to get this result, because you can write f of x star plus lambda, this is f of x star plus this plus some o lambda quantity, and that is greater than equal to fx star. So fx star cancels from both sides, and as lambda goes to 0, you know what this means. I will have this quantity, because here are fx star cancel, we have this, and from here we have this, and then we bypass and move when taking a passage to the limit as lambda tends to 0, I have this. Since x element of C was arbitrarily chosen, we have that this result can be made true for any x I choose in C. So what does it mean? It means the minus of grad fx has an obtuse angle with x minus x star for all x in C, which means that minus of grad fx is actually acting as the normal. That is exactly the definition of the normal cone, that minus grad fx is in the element of the normal cone to C at x bar. For the converse, it's pretty simple, because if you assume this thing, it simply means that for any x in C, this quantity is greater than equal to 0. Then, and applying the convexity, you know what the characterization of a differentiable convex function, then you put any x in C, this is true, then put this to be greater than equal to 0. Then we simply have this for every x in C, showing that it is a global minimizer of f over C. So this is the first result that we learn here. You see, it is slightly tricky, because when you come to a maximizer, the thing is not so straightforward. It is not the same condition. So it says that if you are having a differential function over a closed convex set, then x star is a local maximizer of f if the gradient of fx star is element of nc x star. And if f is a concave function, then x star is a global maximizer. So here x star is a global maximizer if not the negative of the gradient, but simply the gradient must be in nc x star. So it's absolutely a change of sign. It's a very different condition. It's not the same. It's A is not same as B, right? Now let us look into some special cases. A case that is important for economics is the first one, where all the constraints are linear or affine, if you want to say like that. And the second case where C is Rn plus. These two are important to economics. And then we will talk about the case C is an open set, which is of course a mathematical interest. What would happen if the set C is open? How can you deal it when it's a open convex set? Now we will reverse this. When we talk, we will first talk about this, then we will talk about the third one. I think the writing should have been slightly different, I think, and then we should have spoken about this one. Okay. Now, though our definition to the normal cone has been made only for a closed convex set, we will soon see that if we relax it to any convex set, we can still get certain very interesting results. Now let me come to this case. So our this lecture would just done if we just study case 1 now, and our second lecture on this topic we will talk about these cases, because for this particular case we will take a quite some time, because we really need to construct normal cones to Rn plus, because that is the theorem. So we will show in our whole story in this lecture that how normal cone starts playing a crucial and fundamental role when you are talking about problems which are important in economics. Of course, we are restricting ourselves largely to convexity, but let me tell you, things can be slightly different. Okay, so now let us look into this case, that your constant set C is a collection of all x in Rn such that Ax equal to B. Now A is a m cross n matrix, there is no restriction on the full rank or this and that, there is no restriction, and B is in Rm. So once you put a restriction, you are putting a condition. What we are trying to say that when you have linear constraints, you don't have to bother about additional conditions, which you will have to bother about when you come to non-linear or non-affine constraints. Here also you have a linear constraints, but inequality constraints. Here you have equality constraint. But this x belonging to C being non-negative orthant is a very, very important thing in economics, because commodity bundles, this is nothing but the space of all commodity bundles, because you have to choose the commodity from there. So that's why it's very important to discuss this case. But this is such an important case that we'll separately discuss this. That will be our next lecture. So let us just discuss this. So our theorem says that if f is a differentiable function and x star is a local minimizer of f over C, then gradient of fx is element of image of A transpose. Now what would happen is that in this particular situation, the story for the local maximizer would remain the same, because what happens is, because this is a subspace, so if you put minus or you take away the minus, it is the same. Even if you I can write this as minus grad fx star is all in image of A transpose, because if grad fx star is in image of A transpose, then minus grad fx star is in image of A transpose, because image of A transpose, image of a linear mapping, because A transpose is a linear mapping because it's a matrix, image of a linear mapping is always a subspace. So this is, with this knowledge, let's proceed. You might be, I'll just give you a look at the proof. You might be thinking that it is pretty, here we have to use at the end a very important result from linear algebra. So knowing linear algebra is very crucial. That kernel of a matrix is the set of all x for which A of x is equal to 0. So when A operates on x, it gives me the 0 vector, the null vector, the origin actually. So A of x is 0 so we'll collect all those x's, and if you take the orthogonal complement of those vectors, that is to find all the y's for which y of x dot product between y and x is equal to 0. When we find all the vectors perpendicular to all the other vectors in the kernel, then that is exactly equal to the subspace image of A transpose. So kernel of A is a subspace, its orthogonal complement is also a subspace, and that is exactly equal to image of A transpose. This is basic linear algebra. So this is something we want you to know, because this course is a graduate course, and so with this knowledge, let's now start understanding the proof of this. So if x star is a local minimizer of f over C, we will have this. Minus of grad f x star is element of NCX star. So what I'll do, I'll prove that NCX star in this particular case is actually a subspace, which is image of A transpose. That's interesting because it's a cone. And cone, when will a cone become a subspace? It's pretty interesting. So we will simply show that NC x star is image of A transpose. So the cone now is not just a cone, not a set, but a subspace. Subspace is also a cone. So that's pretty interesting. You can so now let V be in the image of A transpose. So what does it mean? There must be a Z for which V is equal to A transpose Z. Okay. Then for any x in C that you have, let us compute this expression V of x minus x star. We want to see whether this V actually lies inside the normal cone. If it is so, then we will know that the image of A transpose is a subset of the normal cone to C at x star, and then we would be left with proving the converse, the other inclusion, opposite inclusion. So once we do this, V is equal to this. So I write V equal to A transpose Z because V is in the image of A transpose, and inner product with x minus x star. Now, by simple facts of matrix or simple facts of life, I would say for optimizers, this is nothing but the inner product of Z into Ax minus x star. But X is element of C. So Ax is equal to B, and x star is a minimizer. So Ax star is equal to B, right? If X star is a local minimizer, then Ax star is equal to B. So which means this V of x in intersection x star is equal to 0, which means V is element of NC x star, and hence image of A transpose is nothing but NC x star. Now we have to show the reverse thing, that whenever W is element of NC x star, we have to show that W is in the image of A transpose. Now W being in the image of in NC x star simply means the inner product of the vector W with x minus x star is less than equal to 0 for any x in C. That's the definition. You observe that because we are having Ax equal to B, right? So that is a closed set. Please understand, Ax equal to B is a closed set. When a set of all x such that Ax equal to B is a closed set. Now, what we are going to show that if you take the closed convex set C and translate it to x star, that is, you shift all elements by an amount x star. Basically, if x star is element of C, now C minus x star will contain 0. In place of x star, 0 will come. So, in the sense where x star was there in the original set C, 0 will come in C minus x star. That is what it means. Now we will show that C minus x star is exactly equal to kernel of A, where kernel of A is this set of all x such that Ax equal to 0. Now for any x element of C, we have A of x minus x star is equal to A. So A of x, let me see what is x minus x star. So x is in C, so x minus x star is in C minus x star. So A of x minus x star is Ax minus x star. Ax is equal to B because x is in C. B minus B equal to 0. So x minus x star is element of the kernel of A. So C minus x star is a subset of the kernel of A. Now take any P in the element of kernel of A. Now we will show that x star P is an element of C because A of x star plus P by the laws of matrices is, because it's a linear operator, is same as A of x star plus A of P. So A of x star is B because x star is the solution, and A of P is 0 because P belongs to the kernel, which means x star plus P is element of C, or P is element of C minus x star, which means the kernel of A is subset of C minus x star, and hence the kernel of A is equal to C minus x star. This simply means now we already have W of x minus x star inner product is less than equal to 0 because W belongs to the normal cone to C at x star. Now instead of x, right, take because x is in C, and you know that x star plus p is also in C for any p in the kernel of A. So replace with x the particular, put x, give x this particular value or particular vector x star plus p, where p is in the kernel of A, where now you will have wp is less than equal to 0 for all p's in the kernel of A. Now this simply means wp, because kernel of A is a subspace, because this is true for any p in the kernel of A, because p is in the kernel of A and kernel of A being a subspace, minus p is also in the kernel of A. So inner product w with minus p is also less than equal to 0, which means inner product of w and p is greater than equal to 0. So combining those two, we will get w inner product p is equal to 0 for every p in the kernel of A, which means that w is in the orthogonal complement of the kernel of A, and we know that the orthogonal complement of the kernel of A is image of A transpose, and hence W is in the image of A transpose. So what did we show? That we showed that the NCX star is subset of the image of A transpose, and proving that, and hence we proved that NCX star is exactly equal to image of A transpose. Now minus of grad fx star is element of image of A transpose by the first theorem, but image of A transpose is a subspace. So if minus of grad fx star is in the image of A transpose, then minus of grad fx star, which is grad fx star, is also in the image of A transpose. So now, as I told you, this is a problem, but this problem is as same as, but the answer you get would be the same even if you replace x star with a local maximizer. So we will stop here for this course, and then we will go to the next one. Thank you very much. That will be in the next class. We'll come with C is open and C is Rn plus. Thank you very much.